Hi all. Let's take a look at the 4.7 Achieve assignment. This assignment is covering optimization, which is going to look to find the maximum or minimum value of some application problem, and just depends upon the specific circumstances of the problem whether the optimum value is the maximum or minimum. So in this first one, we see that the problem is giving us, it says a rectangular bird sanctuary is being created with one side along a straight river. The remaining three sides are to be enclosed with a protective fence. We know that there's 12 kilometers of fence available. Find the dimensions of the rectangle to maximize the area of the sanctuary. Okay, so here's what I did. I went in and I just said, well, I'm going to let one side be the river. That means the other three sides I have to fence in. I went ahead and called the width of this rectangular region X. And I know that I would have to have two sides of that width. So I have X plus X. I knew according to the problem, I had 12 kilometers total of fencing. So the remaining side that's going to be parallel to the river, I'll have 12 kilometers minus these two values of X. So 12 minus 2X. Now I know area of any rectangle is just length times width. So I just said the area with respect to X is X times 12 minus 2X. I went ahead and distributed that X through there and wrote it in descending order. So I have my negative 2X squared plus 12X. Now automatically I know, hey, this is a negative quadratic. Clearly its maximum point, it's going to be at the vertex. So I can go ahead and find that by just saying, well, my derivative of this function is going to give me negative 4x plus 12, just simple power rule. I set that equal to 0. And I know the only critical point will be that point at which this function is maximized. So when you set this equal to 0, you'll get 4x is equal to 12, x equals 3. Now, if you know x is 3, and it's going to ask for the dimensions, so you do have to go back into the problem and say, well, then the vertical side here has to be 12 minus 2 times 3, which is obviously 12 minus 6, or it's going to be 6. And that makes sense. 3, 3, and 6 would sum to be your 12 kilometers of available fencing. And you can see that those are the answers I entered into Achieve. For the second problem here, and in fact, the next three problems I think are like this, pretty simple. They're just giving us two numbers, and they're giving us some criteria based upon them. It says find two positive numbers such that the sum of the first number squared and the second number is 12. And their product is a maximum. So it's a number squared plus another number. That's going to give me a 12. And then their product has to be maximized. All right. So here's what I did. I just said, well, I'm going to let x equal my first number, and temporarily I'll let y equal my second number. Now I say temporarily because you cannot leave this in two variables. You have to get it to one variable. But I say temporarily, I'll put it in terms of two variables because it helps me to solve for one variable in terms of the other. So it said the the sum of the square of a number plus another number was 12. So I got x squared plus y is 12. Now, before I worry about their product, I go ahead and solve for y in this equation. I can say, well, then y is equal to 12 minus x squared. Now, it said that their product needed to be maximized. Well, clearly the product of the two numbers x and y would just be x times y. But I need the product with respect to x, which is why I said, well, x times the equivalent of y in terms of x, which is 12 minus x squared. So now, just like the last problem, I would go through and distribute that x through this group. And when I do, I'll get negative x cubed plus 12x. And I can say, well, the derivative of that equation is going to be negative 3x squared plus 12. I set that equal to 0. That's going to give me 3x squared equals 12. Divide by 3 on both sides, and you'll get x squared is 2. Now, technically, if x squared, sorry, x squared is 4, technically that would give me x is equal to 2 or negative 2, but it said in the problem that both of these numbers are two positive real numbers. So I automatically said, well, it can't be the negative. That's why I just put x equals 2. Now, once I know what x is, I can easily go back and solve for y. Y is just going to be 12 minus 2 squared. That's 12 minus 4 is 8. So I can say my two numbers were 2 and 8, and I don't think it matters what order you put them in. It doesn't. I put them in the order 2, 8 and achieved, thought it was great. For your next problem, again, it's finding two positive real numbers. I'll again let them be x and y, such that they sum to be 96. So I can say, okay, x plus y is 96. And the product of the first and the square of the second is a maximum. So x times y squared needs to be maximized. All right, here's my work on that. I said, well, the sum of my two numbers is 96. That allowed me to say, well, then y is going to equal 96 minus x. Now, the product in this problem was the first times the square of the second. I'm letting y be my second again, and y was equal to 96 minus x. So I can say, well, the product of the first and the square of the second, if I solely put it into terms of x, would look like x times 96 minus x quantity squared. What I did at that point is I just took 96 minus x times 96 minus x. And I got my 9,216 minus 192x plus x squared. I distributed the x through that, and I put it in descending order. I would get x cubed minus 192x squared plus 9,216x. Now I can say, well, all right, you need to take the derivative of this expression. Well, derivative, 3x squared, then I get minus 384x to the first plus 9,216. Now, those numbers didn't really make me too eager to go in and factor that. But I said, well, I can at least factor out a constant factor of 3. That might make it a little simpler, and it did. 3 times the group x squared minus 128 x plus 3,072. But I still was thinking, I don't want to try to factor that by reverse FOIL, by factoring a trinomial. I don't want to have to find factors of 3,072 that sum to get to that. So I instantly just stopped and I said, I'll take the easy way out and use the quadratic formula. The quadratic formula here, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. And you say, well, yeah, you plugged it into the quadratic formula fine. All I did at that point was I went to my calculator, typed this in, took the square root of it, and I was relieved to see that it was a perfect square. And then the square root came out to be 64. So I had 128 plus or minus 64 over 2, 128 plus 64 over 2. That gave me my 192 divided by 2 for 96. And then the 128 minus 64 would give me 64 over 2, which gave me x equals 32. Now, when I think about this, I can say, well, all right, clearly x can't be 96. And you think, why is that clear? Because look at what y would be in that case. If you let x equal 96, y would have to be 0. Their product is certainly not going to be maximized if the second value is 0. It'd be 96 times 0. That's when the product is minimized. Remember, at critical points, it could give you a maximum or a minimum value. So the minimum value actually occurs when x is 96. But I can just say, yep, that's not where the maximum occurs. So I said product would be minimized at x equals 96 because the product would be 0. And it would be maximized if the x, and that's the goal of the problem, if x is 32. And then you could say, well, your y value has to be 96 minus 32. It'd be a 64. Now, it doesn't ask what the maximum product is. It'd be easy to find it, 32 times 64, but it's just asking for the two values that give it in this case. And you can see 32 and 64 is what Achieve wanted. When I go to the next question here, for number 4, again, finding two positive real numbers such that the sum of the first and the second is 34 and their product is a maximum. And this is actually maybe a slightly easier version of number 2. It's pretty much the same problem. So I just say, well, all right, it said the sum of two numbers is 34. So x plus y is 34. I'll go ahead and say y is equal to 34 minus x. And then it said, and their product is maximized. So their product would be x times y. Their product solely with respect to x would be x times 34 minus x in the place of y. And then you can say, well, I could distribute the x through that group and get negative x squared plus 34x. Then I can look at that and say, well, all right, the critical points of this curve are going to occur when the derivative is 0. I know that the critical points will maximize the profit because, again, this is a negative quadratic. It's going to be an upside down u, and its vertex is going to be a maximum. So I can say, well, all right, the derivative is negative 2x plus 34. When I set that equal to 0, I'll get 2x is equal to 34 and x is equal to 17. Now, if you know x is 17, then it's easy to solve for y because it's 34 minus 17. It's also 17. It makes sense that the product is maximized when the two numbers are the same. Obviously, 18 times 16 is not as much as 17 times 17. 19 times 15, even less than 18 times 16. So the further away you get from 17, the lower the product is going to be. So you can say maximum occurs when both numbers are 17. Now, keep in mind, you can't just type in 17 once. You'll have to put it in as both of the answers in this case. So 17 comma 17. Now, number 5 was a little bit of a longer problem. It's part A and part B. Part A, it's asking us to find the dimensions of the box with a square base with a volume of 64 and minimal surface area. So the optimization within this problem is I want to build a box that satisfies this criteria of holding 64 cubic units while at the same time minimizing the amount of materials I'm going to use to create it. That makes sense. Yeah, it's a valiant thing to want to do. You want to minimize the amount of materials. So I can say, all right, my volume formula. Normally, volume of a rectangular solid, we just say, well, it's length times width times height. But it said that this box has a square base. So I let the sides of the base be x. So I just said, well, the area of the base is x by x. The volume of this is going to be that area of the base times the height. So instead of length times width times height, I just said x times h. And I can say, well, all right, that gives me my volume formula in terms of x and h. I'm going to go ahead and solve for h here. I know that the volume has to be 64. So h is equal to 64 divided by x squared. Now, when I use that for my surface area, what you need to be thinking is it's the area of all of the faces of the box. So it's the area of the base, the area of the top. Both of those combined would have an area of 2x squared, since they're both the exact same size, x squared for the base, x squared for the top. And then the 4 faces, well, every single face is going to have an area of x times whatever the height is, h. So there's 4 of the sides, so you'd say 2x squared plus 4xh. That's my surface area formula. Now, I would like that surface area formula only in terms of x. That's what I've done here, because I know h has to be whatever 64 divided by x squared is. So then I go in and I simplify that. My surface area formula is just going to be 2x squared plus 4 times 64 is going to be 256. And then x divided by x squared gives me x to the negative 1. Now, when I'm looking at that, I can say, well, all right, I should be able to take the derivative of this and set it equal to 0. Derivative of the first term gives me 4x. Derivative of the second would give me negative 256 x to the negative 2. I chose to rewrite that as minus 256 over x squared. I set this equal to 0. to find when this function is optimized, when it has its critical point, I can say, well, all right, I can easily set that equal to 0. I'll add the 256 over x squared to the right-hand side. Then I'll multiply both sides by x squared, and I get 4x cubed is equal to 256. Thus, x cubed would equal 256 divided by 4, which is 64. So x is the cube root of 64, which is just 4. Now, if x is 4, then your height would be 64 divided by 4 squared, which is 64 over 16. Hey, that's 4. So then I know that each of my sides of the base has to be 4, the height has to be 4. So this is just saying that your surface area is minimized when the dimensions of the box are a cube. Length times width, or sorry, the length, width, and height are all the same at 4. Now I do believe, let's see, it asked me what the minimal surface area was. So notice, it said side of the base, 4. Side of the height, well, 4. The minimal surface area, so what's your surface area going to be? You just say, well, evaluate your surface area formula at 4, and you'll get 2 times 4 squared plus 256 over 4. Make sure to not use the derivative for it. Make sure you use your surface area formula. And when I do that, I'm just getting 2 times 16 plus 32. That is 2 times 16, 32. And then plus 64, 32 plus 64, 96. And so we can say our minimal surface area is 96, and they never mention units in this problem. You could say square units, but of course, don't write that in. Achieve doesn't want it. For part B here, it's asking us to find the dimensions of the box with a square base with a surface area of 40 and maximum volume. Now, think about this. In order to get that volume of 64, we found that the minimum surface area required to do that would be 96 square units. So now, instead of giving the volume and asking the surface area, they're telling us the surface area or the amount of materials that we have to use. And they're saying you only have 40 square inches of material to use. How much could your volume be? Well, I'm not very optimistic that it would be very large, but we'll find out. So I'm trying to maximize volume given this criteria. So here's how I do it. I go in and I say, well, now this time I'm given information about how much the surface area I have. This is just my base surface area formula, 2x squared plus 4xh. That's going to equal 40. That was my given amount. So now I'm going to try to use this equation to solve for h. And I would get 4xh is equal to 40 minus 2x squared. And then I would just, in order to solve for h, you would divide by 4x on both sides. Then you can say, well, all right, h is equal to 40 minus 2x squared, all divided by 4x. Now, how is that going to go into our volume formula to try to maximize volume? I know that the volume of any rectangular solid with a square base, it's just the area of the base times the height. So volume is equal to x squared h. And then I can say, well, the volume formula with respect to x is going to be x squared times, here's my h, I plug it into my formula. Now, I figured this would be better if I go ahead and distributed the x squared into the numerator and simplified. The first term would be 40x squared divided by 4x gives me 10x. The second term would be 2x to the fourth divided by 4x. Well, 2 over 4 reduces down to minus 1 over 2, and then x to the fourth over x reduces to x cubed. So now I can say, all right, this is a simplified version of my volume formula. I need to find when that is maximized. Excuse me. So I go ahead, I take the derivative, which is easy in this case. Now, I went ahead and took the derivative of the highest term first, so I could write it in descending order. Got my negative 3 over 2 x to the second plus 10, set that equal to 0. It's going to be true when 10 is equal to positive 3 over 2x squared. Multiply by 2/3 on each side, and you'll get x squared is equal to 20 over 3. So x, now if you're solving this out, technically you'd say x could equal the positive or negative square root of 20 over 3. We know x is the length of the base, so it can't be a negative. So we just say, well, it's the positive square root of 20 over 3. And I just left mine as that. Now, that's the side of the base. The other questions that's asked here, that's the side of the base. Well, what's the height? And then what's the volume? Well, the height. I go back into my height function, which was right here, and I plug back in the x value that I know is going to yield the maximal volume. And I can say, well, that's going to be 40 minus 2 times this square root squared, which just gives me 20 over 3, divided by 40 on the square root of 20 over 3. Now, what I did in that numerator is I just said, well, that second term is minus 40 over 3. That first term is 40. So I was thinking, well, 40 minus 40 over 3, that's the same thing as 120 over 3 minus 40 over 3, which would give me 80 over 3. And then that 80 over 3 is divided by 4. 4 goes into 80 20 times. I could leave my 3 down in my denominator. So this was the way I chose to simplify it. Notice I did not rationalize. I think the square root is absolutely fine in that denominator. Now I have my dimensions of the side of the base. I have the height. Well, the volume. I go back up to my volume formula right here, or I could go to this one, either one. And I could say, I'm going to use this since it's the simplified version of it. Evaluate that volume formula at the square root of 20 over 3. I get 10 on the square root of 20 over 3 minus 1/2 times the square root of 20 over 3 cubed. So I'm thinking the square root of 20 over 3 cubed, that's 20 over 3 times the square root of 20 over 3. 20 over 3 times 1/2 is going to give me 10 over 3. And then once I do that, I'm like, ooh, now I have like terms. 10 on the root of 20 over 3 minus 10 thirds on the root of 20 over 3. This is the same thing as 30 over 3 on the root minus 10 over 3. Gives me positive 20 over 3 on the root of 20 over 3, which I think is a gorgeous final answer there. And now notice that's precisely what Achieve wanted for this question. Now, one more that I'll do in this video, and then I'll break up and do the last 4 in another video. They're all a little bit longer. Number 6 here talks about a box again. The thing that differentiates this problem from the box problem before it is we have the cost of materials for the base and the sides. So we have a jewelry box. That's to be built with silver plated sides. So the sides are going to be expensive, but then just nickel plated bottom and top. So the bottom and top are going to be cheap. The volume needs to have 28 cubic centimeters. It says if the nickel plating costs $1 per square centimeter and the silver plating costs $8 per square centimeter, find the dimensions of the box to minimize the cost of materials. Gorgeous problem. Okay, so here's how I would attack that problem. I would say, all right, I'm going to let X be the side of my base. Now, yet again, it said that we had a square base. So the area of my base is just going to be X times X. It's going to be X squared. I'm going to let H be the height. So my volume is, instead of length times width times height, it's X times H, or X squared H. Now, it said in the problem that the volume has to be 28 cubic centimeters. So I set my volume function equal to 28, so I can solve for H in terms of X and say it's just 28 over X squared. Now I go to my cost function and I can say, well, I know that the general formula for the volume of a rectangular solid with a square base is just going to be the surface area formula. We did that in the last problem. That's 2x squared plus 4xh. Well, for each of those square centimeters of area of the base, you have to multiply by the cost. So I said 2x squared, that's the sum of the area of the base and top times its cost, plus this is the sum of the area of all four sides with dimensions xh. So you say, well, you're going to have a total area of 4xh for the sides times the cost per square centimeter, well, $8. So now I'm just simplifying this cost function. I can say, well, it's going to be just 2x squared plus 32xh. Now I need the cost function solely in terms of x. So I'm going to use what I have up here for h and substitute it in. So instead of that last term being 32xh, it becomes 32x times 28 over x squared. At that point, I just said 32 times 28 is 896. X divided by x squared gives me x to the negative 1. Now I'll say, well, I should be able to find when this cost function is minimized if I take the derivative and set it equal to 0. That's what I do. I take the derivative. The first term gives me 4x. The second term is going to give me minus 896x to the negative 2, which I write as minus 896 over x squared. We set that equal to 0. So then I can say, well, that 896 over x squared can move to the right and become positive. And then from this step to this step, all I've done is I've multiplied by x squared on both sides. It gives me 4x cubed is equal to 896. Therefore, x cubed is equal to 896 divided by 4, which is 224. Then you can say, well, then x is going to be the cube root of 224, which is not a nice number. And achieve once this rounded to 3 decimal places. They don't want the exact value this time. So I just said, well, the cube root of 224 is approximately 6.073. Now that's the size of each of the sides of the base, of the square base. The height, and you would expect the height to be very small here because the area for the sides costs 8 times the cost of the top and bottom. So we were expecting it to be a very short box, and sure enough, it is. You can say the height is going to just be 28 divided by x squared. So I just said, well, that's 28 divided by the cube root of 224 squared. And I entered this exact expression in to my calculator. Now, if Achieve wanted the exact answer, of course, that would be it. But Achieve just wants a decimal approximation here in this case. So it was 0.759 centimeters. And you can see that's what I put. Now, again, keep in mind, you never have to put the units because they're already taken care of at the end. Although that should be, oh, no, this is centimeters, not square centimeters. Now, I'll pick up with another video for problems 7 through 10. Let me know if you have any questions.